Alright, so now we're going to do this without a dopey French accent. Today we're going to talk about Le Chatelier's principle. And I still didn't fix this. Alright, so that's the principle of the school, because he's your pal. That's the principle, which is an idea. So Le Chatelier's principle. It's basically a principle that we can apply to systems at a dynamic equilibrium when they're forced to undergo change. The principle is, if a stress is applied to a system at dynamic equilibrium, then the system will move in a way to reduce the stress. Cool. What that means is, if we change it, if we cause a change to happen, it's going to try and unchange it. And that's pretty cool. And when I say try, I'm not trying to anthropomorphize it, because that's wrong and silly. But as a change is forced upon it, it will react against that change. So the factors that we can stress a system with and will disturb the dynamic equilibrium are your temperature, your pressure, concentration, and if it's an acid-base reaction, pH, because that adds hydrogen ions and hydroxide ions, so it's changing the concentration. If the equilibrium moves, it changes the concentrations of the reactants and products. That's pretty straightforward. But the tricky part is, if it moves to the right, and so if the equilibrium moves to the right, that means you'll have more products and more reactants are used up. So if we're over here with reactants, they go to products. Just say we've got an even split 50-50 of each. If it moves to the right, that means the equilibrium will move this way and you'll have more products. If it moves to the left, you'll have more reactants. And as you get more products, it means more reactants are being used up. And as you get more reactants, if it moves to the left or in the reverse direction, you'll have more products being used up. So the concentration will change. And it kind of looks like this. So the changes in concentration are subject to molar ratios. Okay, so they're in proportion. For example, here we have dinitrogen tetraoxide is going to, or decomposing into nitrogen dioxide. So there are twice as many nitrogen dioxide molecules. So you'll see the change when this is where a change is made to the system or a stress is applied, and you'll see that the change results in a double change, so a twice as large change in the concentration of the NO2 because it has twice as many moles of it in the first place. So how does temperature change it? Basically, if the forward reaction is exothermic, these are both exothermic reactions. If the forward reaction is exothermic, if you increase the temperature, it will then move to the reverse direction. It will move this way, because what it wants to do is it wants to react against that increase in temperature. The forward direction puts out, it's exothermic, so the forward direction puts out heat already. So if you add more, it'll move it to the left-hand side and move it over this way. If it is an endothermic reaction and we increase the temperature, now remember the reverse direction in that case would be producing heat. The forward direction would be increasing heat. So if we increase the heat in an endothermic reaction, it will move forward because the forward reduces heat. So amazingly, the opposite is also true. So with an exothermic reaction, if we decrease the temperature, it will move further to the right. Okay? So further to the forward direction. Concentration has a big impact. So if we add or subtract some of the reagents, whether they be products or reactants to it, it results in a shift of dynamic equilibrium. And it will go to the opposite direction of what you've added. So if you add carbon dioxide, so you increase the concentration of one of the reactants, what it will do is it will move the equilibrium this direction. If we decrease the amount, so if we take out some of the carbonic acid, it will also cause it to go this way, because as this is removed, that will increase the concentration over here. If we decrease the concentration of these, so here we're trying to produce nitrogen, and we take nitrogen out, as we just subtract it out, that will cause this reaction to move in this direction. If we increase the concentration of this, which is the same thing, so as we take this out and increase that, it'll also cause it to go in this direction. and that's concentration. Remember, it's going to go the opposite direction of the change you made. Pressure and volume. This relates to gas particles in a reaction only. For example, here, this is a gas. We have 4, so we've got 4 moles of gas for every 2 moles of gas over this side. We have 1 mole of gas for every 0 moles of gas over that side. So if we increase the pressure, and you increase the pressure by decreasing the volume, if we increase the pressure of this system, it will move to the side with less gas particles, which is this side. And if we decrease the pressure, so we expand the volume that the reaction can happen in, it will move to the side with more gas moles. And the reason it does this is to counteract any changes you're making. It's trying to maintain its equilibrium. Now, the dynamic equilibrium will move, but it depends. It'll move in a way that it's trying to counteract the big change you just made to it. So if the number of particles on each side of the reaction is equal, i.e., if it was 1 gas to 1 gas, or 0 gases to 0 gases. So if this was actually an aqueous thing and it wasn't going to come out, if that was an aqueous one, that would make that 0. You can change the pressure all you want. It will not affect the equilibrium. All right. I hope that made sense. If you have any questions, you know the drill. Ask them in the comments below. We'll get back to you as soon as we can. Thanks for watching. Bye now.